Okay, so before we get started with our next topic, we'll just go through a question we left at in the last lecture. So the question was the following. I have 2 point vortices. So this is purely a two-dimensional problem. A point vortex is basically when you have a line vortex that you are looking at as a slice in a plane. So you have these 2 points where there is vorticity, and we know the form of those vorticity. We know what kind of flow it drives. And the question was the following: in scenario one, I have the 2 point vortices having the same sense of circulation. Same sense of circulation implies that they spin in the same manner. Whereas in scenario 2, they have an opposite sense of circulation. So which again says that they spin in the opposite direction. So the question that we had was the following: how should they behave? Do they stay exactly in the same configuration? So if it's an isolated vortex, isolated means if I just look at this particular vortex in isolation, forgetting what is happening in the with the neighbors, it is going to stay where the vortex is initially present, and it is going to drive a flow which goes as gamma by 2 pi r. So there is going to be a velocity field that is azimuthal in nature, which is gamma by 2 pi r. So now what should happen if you have many vortices? Now many is hard thing to do by hand, but 2 is something that we can get a bit of a handle of how to go about it. So as we said, let's consider the vortex on the left. We'll consider scenario 1 first. So this is driving a flow, that is u theta is gamma by 2 pi r. Now if you consider its neighbor, that too, so let me use a different color to distinguish the two vortices. So the neighboring vortex is also driving a flow, that is u theta gamma by 2 pi r. Now let me put some labels. Let's call this the vortex B and this as vortex A. So this is the velocity due to vortex A, this is the velocity due to vortex B. Now what should happen? So we will not do anything very formally as a calculation here. We will try to just see the streamlines and understand what is going on. Now if you remember, the equation for vorticity in 2 dimension is the following: dou t plus u dot del is of the vorticity is equal to 0. In absence of any diffusion, it just follows this equation. So now if you focus on the velocity field due to A, I can keep drawing these streamlines, keep drawing them bigger and bigger, keep drawing them bigger and bigger, keep drawing them bigger and bigger, and eventually you would actually have vortex B in the velocity field due to vortex A. So what you see for vortex A here is that it is experiencing a velocity. So if this separation is, let's say, capital R. So the velocity that vortex at B experiences, so u theta at R equals capital R, which is due to the velocity from the vortex A influenced by or experienced by the vortex at B, is going to be gamma by 2 pi capital R in the theta direction, right? So the vortex B, if you just think of this equation, it is now being swept around by a flow that is azimuthal in nature, which has a strength gamma by 2 pi capital R. So as if it was just a small tracer which is now getting swirled around. But then this vortex B, so now let's detach the two problems. Now vortex B is also driving its own flow, which is of this kind. Each of these streamlines indicate the velocity that is driven by the vortex B at different locations. So now if you were to consider the vortex at A, this guy can also not stay stationary. This chap is also experiencing a velocity due to the vorticity at B from B at the location A, and once again it is evaluated at the same point, that goes as gamma by 2 pi r capital R theta cap. The sense is the same. So now see what is happening. The vortex B basically tries to move in the anticlockwise sense. The vortex A also tries to move in the anticlockwise sense. So finally what you will observe when you have these two co-rotating point vortices, which means they have the same sign. So when you have like signed vortices, they are going to be co-rotating. That means they are going to move in an orbit, where you can now think of that each of these vortices that are there, they are basically moving in a larger orbit. So they will form an orbit and they are going to constantly keep rotating. So this is exactly when the circulation is equal. So gamma A is equal to gamma B is equal to gamma. Okay. So they are equal and like sign point vortices. They are going to move around, spin around each other as if it's in a planetary orbit. Now you can start to think of what is going to happen if the vortices were not point vortices. If the vortices were vortices that had something like, there was a vorticity in a patch and it was, so the velocity was of the following kind. The velocity was u theta was a solid body rotation for below a radius A, and u theta was a point vortex beyond a radius A. Because we saw these two cases, right? We saw a solid body rotation, we saw a point vortex. Now imagine a vortex that is constructed where it's partially solid body, so it has a core that is spinning, and then outside it basically the velocity decays off as 1 over r. So now this has a core which is there. Similarly, the vortex B also, imagine it has a core. It's not a point vortex, it's a vortex of a finite size. Again, this cannot be done exactly as a calculation in a short period of time, but we can start to get a feel of what is going on. So what you can now see, that consider again the vortex B. So the leftmost edge of vortex B, so this particular part of vortex B is experiencing a value. So now if the radius is, if r is the center to center distance between the two vortex and the diameter is 2a, then the leftmost edge experiences a velocity that is gamma by 2 pi capital R minus a. Whereas the rightmost part of vortex B is experiencing a velocity that is gamma by 2 pi capital R plus a. What does that mean? I have this circular patch of vorticity. The left part of that vortex is experiencing a velocity that is slightly higher than what is experienced by the rightmost edge. If I model, so what I am doing here for the purpose of getting an understanding, let's imagine that this was a point vortex, A was a point vortex, and there was a vortex patch at B. So the vortex patch at B, so the picture is the following, there's a lot of clutter there. So there is a vortex patch here at B and there is a point vortex here at A. So at B, you are going to experience a slightly larger velocity on the left side of the vortex than the right side of the vortex, because the left one is closer, the right one is farther away. So which means this thing is going to get deformed. If you again follow this, think of like a blob of dye. The dye is going to get now stretched. So there will be a deformation that will happen of the vortex patch. Now if you extrapolate that argument for now there being a vortex patch here, this too is going to get deformed. So what will happen when you have finite size vortices? If they have the same sign of vorticity, they are going to rotate around each other, but they are also going to get sheared out. So you will have something which will look like, if you are not, if you have some memory from yesteryears, it looks like the Doordarshan logo. You will have a vortex which basically draws out an arm, it forms a filament, whereas the other vortex also draws out a filament, and gradually they will try to spiral around. And once they start to spiral around, the question is, can they spiral forever and keep forming thinner and thinner filaments? And the answer is, we have not explored this in detail, but the answer is always that when things become very small, diffusion is basically going to start becoming important. So eventually there is going to be diffusion, and this will lead to the vortices merging. So this is a very important idea which requires doing sophisticated computation, but physically from an intuition of how vortices behave, you can understand that when you have like-signed vortices that are present, because in an actual problem you will not have point vortices, you will have regions of vorticity. So those blobs or regions of vorticity are going to rotate around if they have the same sign. As they rotate around, if they are sufficiently close, they are going to get drawn out into these filaments. As they get drawn out into these filaments, they will form this kind of a spiraling structure, and eventually they will merge and form one big blob of vorticity. This is an idea of how merger processes happen. Now this was a story for like sign. Now with you already trained with how the arguments are going to go. If this was a vortex which has circulation plus gamma, and this had a vorticity that was minus gamma. So which is to say that if I draw my corresponding streamlines, both would be circular. So these are streamlines drawn assuming that the other vortex is not there. So we are basically considering the scenario that independently what would the streamlines look like. So here the streamline would look going counterclockwise, whereas when it is minus gamma, it is going to be clockwise. Now think what should happen. The vortex on the left labeled as A and the vortex on the right again labeled as B. The vortex on the left is going to have a flow field, whereas the vortex on the right would also have flow field of this kind. Now look at the nature of the flow. So the velocity from the vortex A at B would be just like what we had before. So it would be gamma by 2 pi capital R in the theta cap direction. Capital R is the separation of the 2 point vortices. Now for the vortex at A, which is in the field of vortex, the velocity field of vortex B, you can now see that this is a clockwise spin, which means this particular vortex is going to move with a velocity that is gamma by 2 pi R with a minus sign theta cap. So together, if you see the two vortices, they both have a sense which is going in the same direction. So that means what you will get eventually, that if you have a pair of counter rotating point vortices, they are going to translate. They will just move in a straight path. So you have a pair of counter rotating vortices. These counter rotating vortices, basically if they have opposite but equal strength, they will just move in a straight trajectory. And these are not too hard to do a numerical calculation, because you know that what is the velocity field due to a given point vortex. So the total velocity field will be a superposition of this, and you can actually track what is going on to these individual point vortices. So we will share some numerical calculations that you can play around, and as you can imagine, the picture starts to get more complicated when you have more than 2 point vortices. But this is one way by which people have attempted to understand that if you think of the flow actually being a collection of many point vortices, is that an appropriate way to build or understand what would be turbulence in 2-dimension. So, can turbulence in 2-dimension, can a very disorderly flow in 2-dimension be understood as a collection of many point vortices moving around? So, what you can show this formally is that if you have more than 3, so 4 and above number of vortices, point vortices will display or can display, I should not say will, can display chaotic behavior. So, you can have 4 point vortices if you are not very careful regarding how you choose in placing them. If you just choose them in some random configuration, there is a possibility that they can experience a chaotic behavior. So, this is basically why people have been thinking about, or they have thought about this for quite some time, that is this a minimal model in terms of understanding a turbulent flow in 2-dimension, that a turbulent flow in 2-dimension being, think of it as a soup of many point vortices. So, and there are numerical methods which have also been used, vortex methods which have been used based on this idea, that using it as evolution of many point vortices. Before we close this, regarding this particular picture of 2 point vortices that are counter rotating. Now, here you have a circulation that is plus gamma, here you have a circulation that is minus gamma. So, where do you think this has an application? I mean, obviously, in a collection of many vortices, you could probably have some of different sign, but otherwise, where this is has an application. So, if you extend this, think of a vortex line. So, as I said, a point vortex is basically a straight vortex, a vortex line which has been sliced off and in a plane. So, it is basically the intersection of a plane with a line vortex. So, there is a line vortex. So, let me draw a 2D plane. So, I have a 2 point vortices here, one plus gamma and the other is minus gamma. So, this is a vortex line that is jutting out of this plane. This is a vortex line that is pointing into the plane, right. So, these 2 point vortices which are counter rotating can be viewed as a part of the same vortex line which forms a loop, and we know what that is called, that is a vortex ring. So, if you think of a vortex ring is basically can be, if you take a slice anywhere through the middle of a vortex ring, the 2 things you are going to get are 2 counter rotating point vortices. So, if 2 counter rotating point vortices are going to translate, that automatically tells you at the first point itself that a vortex ring itself is going to translate. We had mentioned this earlier without a strong, just in a slightly hand waving manner, that there is going to be, if you have a curvature in a vortex line, it induces velocity on different segments. Now, what I am trying to convince you with is that a vortex ring, if I take a slice, that is basically 2 point vortices in a plane of different circulation. And we just showed that 2 point vortices of different circulation are going to translate or move in a straight line. So, now if you think of this, this is like as if seeing the vortex ring from the top. This picture is the top view of the vortex ring. So, there is a ring which is coming out of the paper going into the paper, and also there is a part that is hidden below the paper. So, this is why it actually propagates in a straight trajectory. So, when you see smoke rings or vortex rings or bubble rings, if you see them actually propagate, you know fundamentally why they are doing it. You can explain it one way by saying that it is a bent vortex line, and thus there is an induction of velocity from one part of the line on the other part of the line. But you can also get a very simpler, you can get a simpler understanding by thinking of that this, if you were to cut it at the mid plane, the vortex ring is nothing but a pair of 2 counter rotating point vortices, and a pair of counter rotating point vortices will move. They will not stay stationary, they are going to translate, and that is the reason why the vortex ring is also going to translate. So, this is the story that we have regarding vorticity. So, we have gone through this in quite some detail, but still there is a lot that you can do with vorticity. There is a lot that you can understand from vorticity. So, the few entities that we went through, one was we saw point vortices. These are basically singularities of vorticity in a two-dimensional plane. Then we encountered something known as line vortices. So, here it is a point, here it is a line. So, the vorticity is a singularity, but it exists on a curve in space. And we said that this curve can either go from infinity to infinity or end on a surface or a solid surface or a solid surface, or it can close, in which case it is going to be a ring. Okay. You can have more complex three-dimensional structures of vorticities, but these are reasonable things for you to be familiar with, that how vorticity distributions are and how you study them. Okay. So, with that we conclude our discussion on vorticity, which was a way of looking at our governing momentum equation in terms of the spin, how we understand spin, but we can go back to our momentum equation. So, we had our equation which was our starting point for the vorticity. So, we go back to that same equation. I am going to use gravity as my body force, and I am focusing on incompressibility, which means I have an additional equation which is the following. So, this is my Navier-Stokes equation. Now, we are not directly going to jump now to viscous effects. There is still something more to learn with the inviscid equation. So, we will continue with our exercise by ignoring the viscous terms, and that takes us back to an equation, that is the Euler's equation. So, Euler's equation, as you can see, it gives us a relation between the fluid acceleration in terms of pressure gradient and the ambient body force. And this is an equation which as it ignores effects of viscosity does a great job in a lot of problems if you are thinking of either the viscous effects to be very small, speed being very high. So, effectively you are thinking that viscous effects are not dominant, in which case it does a good job if you are away from surfaces, if you are away from body, if you are away from surfaces, which is what we will see that where this equation actually breaks down. So, if you are in the bulk of the fluid and you have viscous effects being very small, Euler's equation, the prediction from Euler's equation does a great job in understanding what is going on. So, if we will attempt at solving one particular problem using Euler's equation. So, this is a problem which some of you might have seen if you have done a fluid mechanics lab. So, there is fluid which at initial instant is filled in a container. The container is placed on a rotating platform. It's rigidly connected to the rotating platform. The platform starts to spin. As the platform and the beaker, entire thing spins, the fluid is set into motion. And then our question is, at steady state, when it achieves a steady state, what does the surface look like? So, if you have not done this, the surface appears in this kind of a curved manner. It gets a curved shape. So, we want to find out what is exactly that curve shape, and the point basically being that how do we arrive at that particular curve shape? What's the exact, how does it depend on, let us say, the rotation of the fluid? How does it depend on the diameter of the container, which let us say is capital, or the radius, the capital R? So, there are few things which we will say here, which is not, I mean, I will jump over them a little bit and we will come back. We are not going to discuss about how this is set into motion. So, we are going to be a little ignorant here and say that we have waited long enough that it achieved steady state, and it has just achieved steady state. The velocity that it attains is a solid body rotation. Which means the angular velocity at any point in r and z. So, I will construct a radial coordinate, an axial coordinate or a vertical coordinate, and then there is an azimuthal coordinate. So, this is a cylindrical coordinate system I am choosing because the container is cylindrical in nature. So, omega r of z is omega, the spin with which the container is rotating. So, there is a constant angular velocity in the fluid. Now, you may ask, how do we know it is a constant? So, if the fluid basically has achieved a steady state, so once it has a steady state motion, the walls are basically driving the motion in the fluid. So, eventually if you wait long enough, all the fluid particles are basically going to spin with the same angular velocity everywhere. Now, to show this with an evidence, we will have to do a viscous calculation. We will have to do a calculation explaining why viscous effects are important. We will have to do a calculation where unsteady or transient effects are important. So, that is not something that we are going to be doing now. We will just say, take this for a fact right now, that the entire fluid is moving with a constant angular velocity. It has achieved a solid state, a solid body rotation system. How does it, once it does that, what should be the shape of the free surface? That is what we are trying to do. So, since we have chosen cylindrical coordinate system, it is more convenient to write our Euler's equation in cylindrical coordinate system rather than in Cartesian coordinate system. So, I am going to do that. So, Euler's equation. So, typically you will find this in most textbooks. There is nothing spectacular about knowing the equation, but the few things which I will like to point out that is important regarding the equation. So, that was my radial component. Now, I am writing my azimuthal component. And I would have one more component, which is my vertical component. And we will consider the density to be constant. So, I am basically assuming this to be constant density. Obviously, incompressibility is anyway there, and we are dealing with Euler's equation. So, now the part which I just want to just make a remark on when I have written down this in cylindrical coordinate system. So, if you know, obviously you have the u dot del u term, that is the term that you have in your usual vector notation. Now, in cylindrical coordinate system, and this is actually true for any curvilinear coordinate system, you are going to get terms which do not have an obvious derivative involved in it. Dimensionally, it is correct. Dimensionally, that term has units of velocity square by length, which is what u dot del u is, but it does not have the form of any derivative. And this is something which you are going to see regularly when you start looking at these conservation equations in curvilinear coordinate system. So, why this comes about? This is obviously got to do with the fact that when you write your u dot del u, you have to remember that u here is, you are r hat, u theta, theta hat, u z, z hat. So when you have the del acting on it, u dot del. So when you have u dot del acting on it, so u dot del would be u r dou dou r, u theta by r dou dou theta, u z dou dou z. When you have these quantities acting on u, we would obviously expect dou dou r acting on ur, dou dou theta acting, or dou dou r acting on ur, u theta, uz. Similarly, dou dou theta acting on ur, u theta, uz, and similarly dou dou z acting on ur, u theta, uz. The additional terms comes about because quantities like dou theta cap dou theta, dou r cap dou theta, these are not 0. The unit vectors in curvilinear coordinate system, they are unit. They have unit length, which means their magnitude doesn't change, but their direction can change. So when you think of a 2D polar coordinate system, if you draw your unit vector r cap and you draw your unit vector theta cap, so as you are at different values of theta, your r cap and theta cap are changing. So at another point, you will have this as your r cap and theta cap. So for a value of theta 1, this is your r cap and theta cap. For a value of theta 2, that's your value of r cap and theta cap, which means there is a variation of r cap and theta cap with theta, which is quite unlike your Cartesian coordinate system, where at any point you are always going to have the same x cap and y cap. So the x cap and y cap direction at any particular point doesn't change. The unit vector in x and y, they don't change with x and y. So which is why you don't get those additional terms in Cartesian coordinate system, but you will always get those terms in curvilinear coordinate system. So this is a small point to actually keep in mind when you are doing calculation in curvilinear coordinate system, that you should get these additional terms, and they will also appear in your Laplacian or the viscous term when you look at it. So that's the story. Physically, what these terms are effectively indicating is you have a centrifugal acceleration that is appearing there. When you are writing it in a curvilinear coordinate system, you will have an additional acceleration that would come by virtue of the fact that you have a flow or you have a velocity component u theta, which is going to drive an acceleration that will be radial. Okay, so that's the way of understanding it from the physical perspective. So now our problem is quite simple, because we have a system that is velocity does not have a radial component. It only has, so this is r cap, theta cap and z cap. So it does not have any z component, it does not have any theta r component, it only has a theta component, which is omega r. And the flow is axisymmetric. Axisymmetric means that there is no angular dependence in theta. When you are having the flow in the beaker, the flow in the beaker looks identical everywhere. So let's look at these terms. So we are looking at steady state, which means all these terms are going to go away. There is no ur. You also don't have any uz, so that term also goes away. You have axisymmetry, which means that term drops off, and this should have been theta, u theta by r, dou dou theta of u theta, so that also drops off. This term also drops off because there is no ur. So finally you are left with an equation where you have a balance in the vertical direction between pressure and gravity. Now the body force is absent in radial and theta direction, because we are only interested in the body force being due to gravity. So the only body force that you have, so your rho g cap is basically minus rho g z cap. So, gz is the z component of the acceleration, which is the body force part, and there is only one component, r component and theta component is absent. Okay, so we are almost there. So, now if I go back to the equations, so I have minus rho u theta square by r minus dou p dou r 0 minus dou p dou z minus rho g. These are the two equations that I have. So, let us integrate them. It is quite simple, and u theta is omega r. So, this equation can also be simplified and we can write it as omega square r square by r. So, it is omega square r is dou p dou r. And here we have dou p dou z is equal to minus rho g. Equation 1, equation 2. So, if I integrate equation 2, I have p of z minus some p naught is equal to minus rho g z. So, P naught is basically the pressure I have at z equals 0. Now, obviously, this will have some function of r, right, because dou p dou z is minus rho g. So, P will have a minus rho g z and then there will be some function of r. So, now if I use this in equation 1, I will have, so P of z comma r actually minus P naught. So, if I now do the integration, I will have dou p dou r is f dash r, which is rho omega square r. So, if I integrate this, I have f of r is equal to rho omega square r square by 2. I can add a constant here, but there is already a constant that is there in P0. So, finally, I have P of z comma or r comma z is equal to P0 plus rho omega square by 2 r square minus rho g z. That is the pressure distribution that you have. Now, we know that on the free surface, this is the free surface. So, the definition of that particular free surface is that it is exposed to the ambient air, and if I say that the ambient air is still, then the pressure at any point from the air side is atmospheric pressure. And we learned this in kinematic and dynamic boundary condition when we learnt interfacial problems, that when you have a two liquid interface, you will have to apply the kinematic boundary condition, you also have to apply the dynamic boundary condition. And in the dynamic boundary condition, we learnt that in absence of any viscous forces, you can have a jump in pressure if surface tension is present. Now, if you discount for the presence of any surface tension, if you say that surface tension effects are negligible, then the pressure inside the liquid at the interface should be the same for the pressure on the other side of the other liquid at the interface, which means P at the interface. So, if this was evaluated at the interface, it should just be P atmospheric. So, you will have P atmospheric on the left hand side. So, at the interface, and so effectively you arrive at an equation which gives you rho omega square by 2 r square minus rho g z is equal to a constant. P naught was some arbitrary constant we chose. Obviously, when you add this to be a atmospheric pressure, you would find that that constant should be equal to your atmospheric pressure that you have. So, all well and good. Now, we have our equation that Z is equal to a constant plus omega square by 2g r square. That is your equation for the free surface. So, which if I have fixed my constants to give me, if this is my coordinate system, that the value of pressure, I am basically evaluating this to be the origin. So, if this is my Z equals to 0, then I will have a free surface that is given as Z equals to omega square by 2g r square, which will look like a paraboloid. So, the free surface is a paraboloid. So, this is a useful way to actually use your Euler's equation to arrive at what the free surface looks like, obtaining what is the shape of that free surface. It is a paraboloid because it is a surface. So, it is a revolution for the parabola about the symmetry axis, that is the Z axis. Now, this particular equation which we have here, even though we chose a solid body rotation. So, the equation that we had in the radial direction was minus rho u theta square by r is equal to minus dou p dou r. So, what this tells us is that p minus of p of r minus p at infinity. So, if I do the integration, so I will have rho u theta square by r dr. So, dou p dou r is rho u theta square by r. So, if I do this integration, this is what would be the expression for pressure, right. So, I will have P of r is equal to P of infinity minus r to infinity rho u theta square by r dr. This gives me what is the pressure at any location, given that I know pressure at infinite distance away by integrating this particular velocity field. Now, what is the significance of this relation? The significance of this relation is, in a lot of cyclones or tornadoes, you have a velocity which is often known from some kinds of measurements. So, what I have drawn here is, let us say, the typical velocity of a cyclone like storm. So, there is an azimuthal flow which starts to increase from the center, peaks at a particular location. So, there is a slightly quiescent core, then it peaks at a particular location and then it starts to decay down. As you go further away, the velocity has basically died down. This is an azimuthal velocity. So, there is a lot of swirl that is happening, a violent amount of swirl that is going on, and this is what you have measured as the velocity. Now, what is important for you on occasions to understand is, how much does the pressure drop at the core of the cyclone? How low is the pressure? Because this plays a big role in terms of a lot of damages, etc., that might actually happen. How low does pressure go at the core of the cyclone? So, here P infinity is P atmospheric. Far away, where there is ambient atmosphere, I can basically replace this as P atmospheric. So, if you have measurements of velocity, you can basically compute how low would pressure get in the eye of the cyclone or the core of the cyclone. So, this is a first level. Obviously, there is a lot that we have looked over. We have said that no viscous effects, no other kind of flow. Obviously, there is a ground that is present. The ground is going to offer significant amount of friction. Besides the friction in the air, which you can ignore, there is also friction that is present in at the ground level, which will basically be responsible for strong vertical and also radial flow. It is not just going to be purely azimuthal. But for the time being, based on what we are learning, you can still use this and get a first order estimate that how much pressure drop would you expect at the core of such violent swirling flows. Because if you have an estimate of this number, you can choose various models, right? You can basically say that I have a certain wind profile in a particular storm is what I have. Based on that, if you were to actually calculate this, you would immediately get a first estimate of what the drop in pressure is. So that's why that relation is actually quite handy. Okay, so I think this is a good place to stop, because what we want to do next is take our Euler's equation and then arrive at something that you all might have come across earlier, which is the Bernoulli equation. So we are going to do it from our Euler's equation. We will start from, our starting point would basically be this equation. So we will start from this in the next lecture and arrive at our Bernoulli equation, and which would be our starting point or gateway into a key part of fluid mechanics, which is studying problems that are devoid of any vorticity. If there is no vorticity in the problem, those are known as irrotational flows. So we will study irrotational flows, and before that we will use the Euler's equation to obtain a relation involving pressure and velocity. So that is where we will focus on in the next class. Okay, so I'll stop here.